I welcome you back to our second part of our lecture A05, where we are looking at equilibrium of rigid bodies. The first part, we're looking at the support reactions and also the steps on how to draw a free body diagram. A free body diagram is very much important for engineers. Before you design, before you solve any engineering problems like our CE2219, you first need to understand the reactions, the support reactions, and you also need to sketch or draw what we call a free body diagram. This time we'll continue with our two-dimensional problems using the basic equations of equilibrium. This example is just asking you to draw a free body diagram. What happens in life? You can look at what is happening. This is a vehicle, right? Now, the idealization of what is happening here, this is the concept where our F, this F is where this gentleman is standing. Where you can see this pin connection, this is supposed to be here. This spring is representing that, and that steel bar is representing that. Then the angle which moves from A to B is also representing as that A to B. Now, how do you draw this free body diagram? That is the first thing that you need to look at. What are the external forces, external reactions that I'm supposed to look at? So, of course, you have a pin connection, you have your load, you have another pin connection, you have a spring normally reacts like some sort of a rope. So we have another reaction there. A pin connection, all of us, you can remember that you need to have two reactions, the other one in the horizontal, the other one in the vertical. That is, if we say that is the X and that is the Y. This is how it looks like, where you have your reaction, then you have your spring, and you have another load there, and the load that has been applied as F. That is how your free body diagram looks like. Another example. Two smooth pipes, each having a mass of 300 kgs, are supported by the forked tines of the tractor as shown. Draw the free body diagram for each pipe and both pipes together. Now, if you can remember, what is really happening on these pipes? The key here is two smooth pipes. So once they say it is smooth, this simply means they are not prevented from translating in one direction. We have been given the mass of 300 and the forklift itself is the one that is supporting the 300 kg pipes. So when you have a look at this, of course we know the weight is always supposed to be on the center, and another one that is 300 kgs times 9.85, right? Then what do we have here? It's also a smooth arrangement. So we're only going to have another force there, which also applies to another force there, which also applies to another force there. And don't forget always to define your axis, X and Y. Then what about here? What is happening? Even here is the same arrangement. We have one there and another one there. So this is what normally happens in reality, but when you come to class, we try to come up with some sort of idealization on how to represent such type of questions, such type of problems. I meant which is supposed to be here. That's where that T is coming from. That R is coming from this other pipe, which is that reaction. And that F is this support here. And of course, there's another support, which is a P. And let us not forget about the self-weight. That is how you draw the free body diagrams. Another question. Draw a free body diagram of the crane boom which is supported by a pin at A and the cable BC. The load of 1,250 pounds is supported at B and the boom weighs 650 pounds. Forget about things that are not necessary. Already we know we have the load, we have the boom itself, and we have a cable. And the boom itself, and we also need to know how is this thing being supported. It's also important. You also need some reactions here. And if you can remember on those steps, on how to draw a free body diagram is going to tell you what exactly are you looking for. So for me, I have the reactions where the wheels are and the other reaction that I'm going to have at B, depending on what exactly I'm looking for. Since I'll be given the load of 1,250 pounds, it will be easier for me when I'm doing my analysis to start with this point, because at least I have got one known. I have got one parameter which I know. The second one, you can even see that there is a moment there. This is a roller. If it's a roller, we always know that we need to have a vertical reaction. Always. Always, we need to know that we have a vertical reaction. Here we know that that's a pin. A pin connection, we need to have two. The vertical and the horizontal. And we know very well that this guy is not being prevented to move either this direction or that direction, but is being prevented to move in this direction or the other direction. So we only need one force. And let us not forget about our load. Let us not forget about our load. Let us not forget about our load, which is our... This is how the reactions look like. This one is simply showing us that instead of including the reactions that are coming between the wheel and the surface of the road, you can as well isolate the boom itself, where we have been told that there's a pin connection. Depending on what you have been given. This is just like what I was explaining. This is what you are going to have. But now, when you look at how the free body diagram have been drawn, is whereby they have isolated, they have only used the member C, B, A. But if you consider all the members, that is A, B, C, D, here we know that there is a pin connection. Depending on what you are looking for, you can even start from D. Once you have D, then you come to the member C, B, A. You will learn more, and there are more questions that are coming when we start lecture 7, where we are looking at structural analysis, more especially frames. This is what you'll be. This is how you'll be calculating and drawing your free body diagrams before you get your reactions or the forces within each member. Equilibrium condition for 2D. We know that in 2D we always have our usual X and Y. So the condition of equilibrium will define as a condition in which the resultant of all forces and moments acting on a body is 0. So that is the summation of forces in the x, summation of forces in the y, and the moments about any specific point. In this case, it can be a 0. That will be the center. Supposed to be equals to 0. That is the condition that we always supposed to apply or to use when you are calculating our problems. Categories of equilibrium. Here is just a table just trying to make you understand what type of categories do you have for equilibrium. The first one, it says collinear. If the forces are collinear, what are the equations that you need? If they are collinear, you know it can be in the x-axis or it can be in the y-axis. Then you only need one equation, which can be summation of forces in the x or summation of forces in the y is equals to 0. Why is it like that? Because if I say summation of forces in the y, it will be your forces that you can see there, F1, F3, and F4. They have got a 0 component in the y-axis. But if you'd want to make things a bit exciting, instead of using the x-axis along the collinear forces, you can put your axis to be your x and y. If you define it like that, this will simply mean you are going to have, instead of one equation, you are going to have two, which is summation of forces in the x and summation of forces in the y, which also applies for concurrent forces at a given point. You are going to have two equations, summation of forces in the x, summation of forces in the y. If they are parallel, you need two equations. That is, of course, one summation of forces in the x and summation of moments about a specific point. Meanwhile, in general, if you have forces like the way they are, F1, F2, F3, moment, we always need to apply the three basic equations of equilibrium. That is summation of forces in the x, summation of forces in the y, and the summation of moments about a given point. If you can't remember all these in terms of the categories, it doesn't matter. Just know that there are three equations of equilibrium for the condition of equilibrium in 2 dimensions. So you can start with summation of forces in the x, then you're going to find your components. They are all in the y-axis. That will simply mean your summation of forces in the x is not applicable. You do the same for summation of moments, you say it's not applicable. Like in the case of forces which are collinear. Wherever you'd want to calculate your moment, like maybe you'd want to get your moment about this point, you can't find that perpendicular distance, because for you to multiply, for you to get that moment, you need to calculate the force times the perpendicular distance. But in that case, you can't find it. So which will simply mean the moment equation is not applicable. So don't memorize to say if it's collinear, I'm supposed to use this. It's concurrent, I'm supposed to use this. Just remember, take it that is always a general condition. And there are these three equations that you are supposed to apply. Alternative sets of equilibrium equations. We know that summation of forces in the x, in the y, and moment is equals to 0 are most often used for solving coplanar equilibrium problems. Those are forces along or on one plane. Two alternative sets of three independent equilibrium equations may also be used. One, such as summation of forces in the x, summation of moments about A, summation of moments about B is equals to 0. The second one is summation of moments about A, summation of moments about B, and summation of moments about C is equals to 0. How do you arrive at these alternative equations? When you look at our figure A, you have F1, F2, F3, F4, you have A and B. If you say summation of forces in the x, you are only going to have the component of F2, the component of F4, the component of F3. You won't have any component of F3. If you say summation of moment about B, if I get my moment about B, it's supposed to be equals to 0. Always remember that this body, it is in equilibrium. So this can also work if I say summation of moments about A, summation of moments about C. Once you do that, then you find your resultant, force and moment. Find time to prove that this can also be used to calculate our problems. Two and three force members. Conditions for a body to be in equilibrium under two forces are forces must be equal, opposite, and collinear. Note that the shape of the member does not affect this simple requirement, and the weights of the members are assumed to be negligible compared with the applied forces. Starting from our lecture 1 up to lecture 5, we have been assuming mostly that the members have got a negligible weight. But the upcoming lectures will also be considering the weight of members. But this is just trying to make you understand, trying to reduce the number of unknowns, trying to reduce the number of factors when you are calculating the reactions or when you are calculating the forces. The second situation is a three-force member, which is a body under the action of three forces. We see that equilibrium requires the lines of action of the three forces to be concurrent. This, for a body to be in equilibrium, where three forces has been exerted on that body, needs that those forces, the lines where the forces have been applied, supposed to be concurrent. This is what it means. If they were not concurrent, then one of the forces would exert a resultant moment about the point of intersection of the other two, which would violate the requirement of a zero moment about every point. The only exception occurs when the three forces are parallel. Only when the three forces are parallel. Sometimes I normally bring in some multiple choice questions, just asking if you really find time to read and to understand. In this case, we may consider the point of concurrency to be at infinity. Constraints and the statically determinacy. The equilibrium equations shown in this lecture are both necessary and sufficient conditions to establish the equilibrium of a body. However, they do not necessarily provide all information required to calculate all the unknown forces which may act on a body that is in equilibrium. The equation's adequacy to determine all the unknown depends on the characteristics of the constraints against possible movement of the body. What it means here is the constraint is the restriction of movement of that body. A rigid body or rigid combination of elements treated as a single body which possesses more external supports or constraints than are necessary to maintain an equilibrium position is called statically indeterminate. Note that if you have more external supports or constraints that are necessary to maintain an equilibrium, that system or that body, that member will be called statically indeterminate. Supports which can be removed without destroying the equilibrium condition of the body, they will be called redundant, but they are useful. When you do your calculations, you don't need those members, right? But you would need the redundant members for the purpose of stability. The number of redundant supporting elements present corresponds the number of redundant supporting elements present corresponds to the degree of statically indeterminacy and equals the total number of unknown external forces minus the number of available independent equations of equilibrium. Bodies which are supported by the minimum number of constraints necessary to ensure an equilibrium configurations are called statically determinate. And for such bodies, the equilibrium equations are sufficient to determine the unknown external forces. Statically determinate bodies, you only need the basic equations of equilibrium to solve or to find the unknowns. We must be aware of the nature of the constraints before we attempt to solve an equilibrium problem. A body can be recognized as statically indeterminate when there are more unknown external reaction, then there are variable independent equilibrium equations for the force system involved. What this means is, if you have, as an example, we are still in 2D. If you have your three equations, summation of forces in the x should be equals to 0, summation of forces in the y should be equals to 0, and summation of a moment should be, summation of a moments about a point should be equals to 0. Those are the three basic equations that we have. This simply means we need as well to have equal or less number of unknowns. That simply means we need to have 3 unknowns or less. If we have more than 3 unknowns, then that system will be called statically indeterminate. You can't solve that problem simply by using the 3 basic equations of equilibrium. It is always well to count the number of unknown variables on a given body and to be certain that an equal number of independent equations can be written. Otherwise, effort might be wasted in attempting an impossible solution with the aim of the equilibrium equations only. So here, I'm just trying to show you statically indeterminate reactions. We have A, where we have more unknowns than equations. We don't know P, we don't know Q, we don't know S. Even if we get the components in the X and Y, we are going to have 6 unknowns, which will be 1, 2, 3, 4, 5, 6, plus the reaction itself. Here we have got a pin connection and here a pin connection. So we are going to have another unknown, another unknown, and another unknown, giving us 10. And the weight of the member itself, making 11 unknowns. Meanwhile, we only have 3 equations of equilibrium. You can't solve this problem just by using those 3 basic equations of equilibrium. When we got the second one, it still has forces, that is P, Q, and S. But the reaction here is a roller. Yes, here I've got fewer unknowns than equations. This is partially constrained. The last one, we still have the force P, Q, and S. And we have rollers at A, E, and B. Here we have got equal number of unknowns and equations, but improperly constrained. Example. Question. Determine the magnitude of the forces C and T, which, along with the other 3 forces shown, which act on the bridge-truss joint. The first thing that we do, we look at how many unknowns do we have. One, of course, we don't know the magnitude. 2, we don't know T, we don't know C, but we know the 3 other forces, that is 3 kilonewton, 16 kilonewton, and 8 kilonewton. And we also know the angle between the T, where the force T is passing, and where the 8 kilonewton is passing. To solve this problem, you can either use the scalar method or the vector method. The vector method, this is where we are going to use the unit vectors, the I and J. This is two dimensions. The first thing that we do, we need to analyze which system of axes is easier. Is it the xy or the x prime y prime? It doesn't matter. You can solve this problem by using either the x and y or the x prime y prime. Always remember, this already is showing us this is like a free body. This is like a free body diagram. So there's no need of drawing. This is just more like a free body diagram. We only need to apply our basic equations of equilibrium. And when you look at this question, is it not concurrent? Because all those forces, they are coming from the center, or is coming from or going to the center, which simply means these forces are concurrent. So how many equations are you supposed to use? It will only be summation of moments in the x and summation of forces in the x and summation of forces in the y. Those are the only equations that you use for you to calculate your magnitude, your C and your T. So the solution, the given sketch constitutes of a free body diagram of the isolated section of the joint in question and shows the 5 forces which are in equilibrium. So if you use the x and y axis, you use your summation of forces in the x is equals to 0 and summation of forces in the y is equals to 0. You are going to have equation A and equation B. Then you apply your simultaneous method, you will find your T and C. You can as well use the x prime y prime. You do the same summation of forces in the x and summation of forces in the y. If you still you'd want to go further, you can even use the vector algebra. The vector algebra, it will be summation of forces to be equals to 0. Because for here we know, when we talk about summation of forces is equals to 0, I mean the I and the J. Then at the end, I need to use the I to be equals to 0 and the J to be equals to 0. You solve those two equations, you would find the same answer, your T and your C, to be 9.09 kilonewton and 3.03 kilonewton respectively. Another example. Question. Calculate the tension T in the cable which supports the 500 kg mass with the pulley arrangement shown. Each pulley is free to rotate about its bearing, and the weights of all parts are small compared with the load. Find the magnitude of the total force on the bearing of pulley C. If the question says each pulley is free to rotate about its bearing and the weight of all parts are small compared with the load, this simply means the load of the pulley is negligible. So we don't consider that. First thing first, at A, if I call this tension A, this would be the same tension in this. This is the same rope. So this will also be TA. Right? Then when I go to pulley B, this I can call it TB, which will be the same as tension TB. Right? How do we calculate the load of that 500 kilonewton? It's just by multiplying that times our 9.81. Then, once I've got that, I can now draw my free body diagram. How am I going to draw my free body diagram? I'm going to start from A, not B and not C. Why? If I start from C, I'm going to have a lot of unknowns. I'll get stuck. When I go to pulley B, I'm going to have two unknowns, TB and TA. I'll get stuck. But when I start with pulley A, I'm only going to have one unknown, which is TA, because I already know the 500 times 9.81 Newton. So, the first free body diagram, it will be easy to draw that, and that, of course, this is where we have our pulley, something like that. This is our TA and TA, and we have our force, which is your 500 kg times 9.81. We do our summation of forces, that is if this is our X and this is our Y. We say summation of forces in the Y should be equal to 0. 2TA would be equals to F. TA would be equals to 500 kilonewton times 9.8 divided by 2. This is how simple it is. The solution. The free body diagram of each pulley is drawn in its relative position to the others. We begin with pulley A, which includes the only known force, as I mentioned. So don't start from maybe a point where you have got a lot of unknown. Try or start where you have one known force. That is your starting point. In this case, which was pulley A. Another example. Question. The uniform 100 kg I-beam is supported initially by its end rollers on the horizontal surface at A and B. By means of the cable at C, it is desired to elevate end B to a position of 3 meters above end A. Determine the required tension P, the reaction at A, and the angle. This is supposed to be theta, the angle between the I-beam and the flow. What this means, A will remain wherever it is. The I-beam will be something like that. Then here we are going to have our P. Of course, here we are going to have our 3 meters, which is the distance from here to there. We are looking for this angle. We can call it theta. And don't forget that the I-beam is 100 kg weight. So we also need to consider the self-weight, which will be the 100 times 9.81. What do we have at A? Is it a pin connection? Is it a roller? Here you have been told that these are rollers. So rollers, we only need one support. You can call that maybe force A. Then you have your P. You have your 100 times 9.81. You apply the basic equations of equilibrium. Summation of forces in the X, summation of forces in the Y. You'll be able to get the tension P. And we know the distance between the I-beam and we know the 3 meters, so we can calculate the angle. This is how simple it is, just by applying equations of equilibrium, summation of moments, summation of forces. And you get your P, you get your P, and you get your theta. Another example. Determine the magnitude T of the tension in the supporting cable and the magnitude of the force on the pin at A for the jeep crane. For the jeep crane shown, the beam AB is a standard 0.15 meter I-beam with a mass of 95 kg per meter of length. Understand the question. Once you understand the question, find the unknowns. How do you find the unknowns? By drawing the free body diagram. Once you draw the free body diagram, you apply your equations of equilibrium. summation of forces in the x, summation of forces in the y, and summation of moments should be equals to 0. This is how your free body diagram looks like. You can note that at A we had a pin connection. A pin connection, we need two reactions. That is one horizontally, one vertically. That is, of course, in the X and in the Y. A rope, we know, is always in tension and is normally represented in this manner. You have got three unknowns, AX, AY, and T. If we say summation of forces in the Y, summation of forces in the X, summation of moments, you will get stuck somewhere. But once you apply the summation of moments about A, you get rid of the two unknowns, that is the AX and AY. Then you're only going to remain with one unknown, which is T. Then you'll be able to get your T. Now, once you have your T, that's when you can now apply the summation of forces in the X, the summation of forces in the Y. This is our second break. We will continue. The last part is just a build-up of what I was teaching, except it will be now in 3D. I'm just adding the third axis, which is the Z axis. So instead of having the basic three equations of equilibrium, when you go to 3D, you end up having summation of forces in the X, summation of forces in the Y, summation of forces in the Z, summation of moments in the X, summation of moments in the Y, summation of moments in the Z should be equals to 0. So, what I just taught you, I'm just adding the third axis, which is the Z axis, but applying the same principles. I end here for now.